Welcome. This is the second part of the lecture. These two lectures are an elaboration of this review article that I've already shared with you. So the overall goal of these two lectures is to illustrate how doped oxide catalysts can be used for undertaking oxidation catalysis. Okay, doped oxide catalysts. We'll use some case studies to demonstrate how doped oxide catalysts can be used for specific oxidation reactions like CO oxidation, preferential CO oxidation. What do you mean by that? There is a mixture of carbon monoxide and hydrogen. Despite there being two gases, you are going to only oxidize carbon monoxide to carbon dioxide and not wanting to oxidize hydrogen to water, of course. So why is this important? Much of hydrogen is being generated, for example, from hydrocarbon resources. Okay, when you do generate hydrogen in that manner, so byproduct is carbon monoxide. Okay, and that's many times carbon monoxide is a poison. For example, this hydrogen, when supplied to fuel cell, for example, carbon monoxide poisons the electrocatalyst. So before supplying hydrogen to fuel cell, you want to purify the gas stream by preferentially oxidizing carbon monoxide to carbon dioxide. Okay, so all these things are important oxidation reactions, and carbon doped oxides have been explored for undertaking these kinds of reactions. So we'll do some case studies here. In the first part of the lecture, we looked at density functional theory. Okay, so I'll quickly go through all these things because we have done this in the last lecture. We talked about two approaches to modeling surfaces. One is called cluster approaches, which evolved from quantum chemistry, and slab supercell approach, which evolved from solid state physics. And then we looked at two important theorems, which eventually resulted in Nobel Prize for Walter Kohn, how to compute energy of an electronics as a medium containing electrons and nucleus. And it was mentioned that energy is a unique function of electron density. Electron density, that uniquely determines energy. All right, and then even though this is an important theorem, this doesn't tell you how to obtain electronic density. Okay, so that was illustrated using the Kohn-Sham approximation, wherein single electron wave functions called Kohn-Sham orbitals are used for building up the electron density, which in turn determines the energy. All right, so and we elaborated, these are two fundamental aspects of density functional theory, which made it practical. And there are other ingredients, okay, so called 3 P's. Okay, one is plane waves. Okay, these are basis function, elementary function that are used for representing Kohn-Sham orbitals. The Kohn-Sham orbitals are expressed as a sum of many plane waves, and the square of the plane wave, square of the Kohn-Sham orbital gives is a measure of probability of finding an electron. So which in turn determines electron density. All these things again are elaborated in the review article. And what is the other P? Another is the periodic. In the last slide I told, it's the periodic systems. Okay, so most of the condensed matter systems, solids and so on, are large systems which are represented using periodic boundary condition. That is the second P. The third P involves pseudopotentials. Okay, the core electrons are not important for chemical bonding. Only the valence electrons are represented exactly, and the core electrons are represented using a pseudopotential. So these are 3 P's. Okay, so we also tell the validity where DFT is most valid, and then we also told the last lecture that when you're thinking about quantum mechanical system, everything is represented using a Hamiltonian operator. We elaborated each terms of the Hamiltonian operator. This is useful for estimating the total energy of the system. Okay, the expectation of the Hamiltonian. Okay, when I say expectation of Hamiltonian, this is the object I am talking about. This is a normalization condition. This will give me the total energy of the system. All right, and we also elaborated these things yesterday. Decompose the total energy into different parts, and these are the mathematical expression for the different parts. And one of the most important parts, okay, which are essentially quantum mechanical. So in this part, there are all these three are classical. There are classical equivalents. Okay, kinetic energy, Hartree energy is a repulsion energy between electrons, and the attractive energy between electrons and ions have classical equivalents. However, this is completely quantum mechanical in nature. Okay, because the electrons are fermions, there is an exchange interaction, and we'll also see what is correlation interaction in the next few weeks. And then all these things are put together, and the expression for the Constam approximation is given here. Again, the basis for pseudopotential was explained in the previous lecture. When all these things are done in Fourier space, okay, so the expressions may become complicated. Okay, so it's mathematically you can address this, but this just to give you an idea of the mathematical expression when you express everything in Fourier space using, okay, because the plane waves are the basis functions which we are going to use here. And then this is the overall algorithms. Okay, so algorithm used for density functional theory. This is where we stopped in the previous lecture. So this lecture will be essentially on catalysis using doped oxide systems. So what are the important, as chemical engineers, we should know what are the important issues we are dealing with in heterogeneous catalysis. Typically, chemists address issues of homogeneous catalysis, where the reactants, catalyst, and the products are in the same single phase. Okay, so this has issues with separation of products from the catalyst and the reactants. So homogeneous catalysis is useful for synthesizing certain systems in the lab scale. Okay, they are still used in industrially, but industrially the most common catalysis is heterogeneous catalysis. So what is the essential difference here? In heterogeneous catalysis, the products and the reactants are in different phase compared to the heterogeneous catalyst. Okay, so there is an essential advantage in terms of separation of the system. Okay, there is a solid catalyst, for example, ammonia synthesis catalyst. The catalyst is a solid, reactants nitrogen, hydrogen, or gases, and the products ammonia is also a gas. Okay, so there is an essential advantage in terms of separation. Okay, so the present challenges in heterogeneous catalysts are, so typically the feedstock, okay, and the energy source, okay, these are the things that are being replaced into newer feedstock and newer energy sources. Okay, so most of the feedstock we talk about petrochemicals. Okay, we could have also talked about coal chemicals. Okay, so okay, what do you mean by that? Coal chemicals, the feedstock, the materials, coal is processed into further chemicals. In petrochemicals, petroleum is being processed into further chemicals. Okay, so when you say petrochemical industry, there are two aspects to it. Okay, both in terms of feedstock, petroleum is being processed. Also in terms of energy, petroleum is being used. Okay, so typically these are, petroleum is replaced by natural gas, and in some cases coal. Okay, so that is also not good. Okay, all these things. Okay, coal is very bad in terms of global greenhouse gases. So petroleum is slightly better because of the scarcity in petroleum. We may use for some feedstock instead of petroleum coal, but that's also not a good choice because again we are going to produce greenhouse gases. Natural gas is better, okay, in terms of CO2 generation compared to coal and petroleum. Again, this also results in some amount of CO2, so that is also not good. Okay, ideally we should be able to not only use renewable sources for both feedstock and energy. What do we mean by this? Okay, so one part, renewable energy must be, you must be all familiar with that. You're using, let's say, solar energy, wind energy, and so on as energy source. As opposed to this, there is this other aspect which as chemical engineers we should be familiar with, which is to do with feedstock. Okay, so what is an ideal renewable feedstock? So there is a lot of emphasis on what is called biorefineries. What do you mean by that? So we are using plants, we grow plants, okay? This is much greener, and the plants essentially have hydrocarbons, right? So instead of using petroleum as a feedstock, you are using bio plants as a feedstock. So there's a lot of emphasis on trying to replace the entire chemical industry with both renewable energy sources as well as feedstock also is renewable. So there are lots of design of biorefineries. Maybe we'll try to do in some cases, okay, what this actually means. In your CRE class, you might have seen all these things. So the emphasis here is on how to generate chemicals from non-traditional feedstock. That is very important. So there is going to be penalty for generating greenhouse gases. Okay, in the last century, there was no penalty for chemical industries producing the pollution. Okay, generating pollution. But now I think there is a lot of environmental awareness on these issues. So if you generate CO2, you're going to be penalized. There's going to be a carbon tax. Though the actual magnitude of the carbon tax is not clear, but that's going to affect chemical economics. Okay, so there's a lot of emphasis on what is called green technology. Okay, and so ideally, we want to be using two aspects. Okay, we want to be emphasizing two aspects. One is the chemical routes have to be selective. Okay, so we don't want to be producing a lot of waste products, and the chemical routes preferentially should be operated at low temperatures. Okay, they are not then energy intensive. Okay, these are, and of course they have to be stable for a long time. Okay, so selectivity and low temperature processes are going to be play greater important in chemical industries. So in few lectures ago, so I talked about a particular volcano principle, Sabatier principle. I've elaborated in the previous lecture. So again, I'm just revisiting this topic in the context of doped oxide catalyst. Okay, so what are we talking about? We are talking about doing oxidation. Okay, so see, if you want to think about forming a reduction system, let's say you want to add hydrogen to let's say in the case of, let's say, methanation. Okay, so you typically use metals. Okay, on the surface of the metals, they could have been metal hydrides that could have been formed. So as opposed to that, when you talk about oxidation catalyst, even if you start your catalyst is let's say a metal. Okay, so this was very elaborately demonstrated on ruthenium catalyst. Okay, supposing I want to be oxidizing carbon monoxide to carbon dioxide, I start with a metal, let's say ruthenium. In the initial, when you supply oxygen, what are the first step? The first step is the oxygen is not used for oxidizing the reactants. Okay, the oxygen goes towards oxidizing the metal to metal oxide. Okay, so even though you may start with metal during the course of the reaction, in the first few hours when you run the reactor, what happens is the metal gets oxidized to metal oxide, and metal oxide is the real catalyst. Okay, so in the chemical industry, when you start a reactor, the products that are generated in the first few hours are usually not used. Okay, so you don't even collect it, you vent it out, because in the first few hours of the reactor, what is happening is the catalyst gets modified, okay, from an inactive form to a more active form. Okay, so that is so in this case, let's say you start with the metal, you convert it in oxide, which is the active catalyst actually. Okay, so how do you think about designing new catalyst from an oxide? we are talking about dopant. You have metal oxide and you use a substitutional dopant. We have elaborated this in a previous lecture. The dopant makes the oxygen atom more control the activity. Okay, so what you want to do, the dopant, when you use substitutional dopant, okay, you have a dopant which is let's say a cation, which is replacing one of the host cation and therefore activates oxygen atoms near the dopant. Okay, so that has an important role in modulating how easily oxygen vacancies can be created. So if it is too easy to create oxygen vacancy, that is, the oxide gives off oxygen very easily, you don't have an oxidation catalyst. You just have an oxidant. Okay, for example, KMnO4, potassium dichromate, they're all good. They're not oxidation catalysts, but they just supply oxygen to the system. Okay, so this is not a good oxidation catalyst because it's going to be hard to reoxidize the oxide. Okay, so the general idea here is oxidation catalyst. Okay, if you want to have an oxidation catalyst, you want to be here. So if it's too easy to, this is on the x-axis, we are talking about some measure of ease of oxygen vacancy formation. Okay, how easily the metal oxide is going to supply oxygen to the reactants. Okay, if it's too easy to supply, you just have an oxidant. You don't have an oxidation catalyst. If the oxygen vacancy formation is very high, it is very hard to give off oxygen. Okay, so a good oxidation catalyst is one in which oxidation oxygen vacancy formation energy is not very less or very high. Okay, so you want to be in this region. Okay, so that's what that's the governing design logic for this system. Okay, so for example, so this, what are we seeing here? I'm looking at the host oxide is zinc oxide. So typically these red spheres here indicate oxygen atoms, whereas these gray spheres indicate the zinc atoms of the host catalyst. And then what I'm trying to do is I'm replacing, in this case, the dopant is gold atom. This catalyst, this metal oxide has, let's say, a small percentage, can be just 1%. Okay, 1% of the metal host atom is replaced by gold atom. Let's say that is the dopant. Okay, gold is expensive. You don't want to be using a lot of it. And then what does it do? When I do that, the dopant affects the oxygen to which it is bound. Okay, this oxygen which is bound to the gold. I mean, if there's if this was an in-person class, I would have asked this question. Okay, what do you think is going to happen to this oxygen atom? Okay, intuitively, you know that gold does not want to be forming a gold oxide. Okay, you might have the common oxide which you have heard, for example, zinc oxide. Okay, it's a common oxide because if in your childhood you might have used something called lactocalamine. Okay, these are calamine lotions, skin lotions. Okay, when you have a skin rash, you might have used this lotion. Lactocalamine has zinc oxide in it. Okay, titania. Okay, is common oxide. Other most common oxide which you must have surely encountered is iron oxide, which is just rust. Okay, these are all common oxides, and none of this have expensive metals in them. Okay, zinc, titanium, iron, these are all not expensive metals, and they form oxides very easily. But you might have not seen gold oxide. Okay, if that is there, you're in trouble, right? Most of your gold jewelry does not form a gold oxide. It continues to remain as gold. Okay, so because gold does not want to form gold oxide. Okay, so intuitively you might anticipate that this bond between oxygen and dopant gold here is going to be weakened. Okay, so when I introduce gold onto this, I am weakening this bond. Therefore, I am making facilitating this oxide, doped oxide, to give off oxygen. Okay, so the oxidant capability of this metal oxide is going to be enhanced. Okay, so that's the way you are thinking. Okay, so when I do that, I have formed an oxygen vacancy. Okay, so let's just compare. Okay, I had an oxygen here, and I have created an oxygen vacancy. That's a vacant site. Okay, that oxygen has been given can be given off to a reactant that needs to be oxidized. Okay, so that's the general principle. And then I've just talked about one part of a catalytic cycle. Okay, I've given off oxygen, but the other part of a catalytic cycle is to oxidize. Okay, so that's the other part. So in this study, what is the goal? Okay, this is something which I did as a postdoc long time ago. What were we trying to see? What is the measure of understand the logic. Okay, so in all these cases, there's a descriptor. Okay, so for oxidation catalysis, okay, all the reactions, okay, methanation, many reaction, okay, all these things we are going to be talking about descriptors. Okay, so in this case, oxygen vacancy formation energy is a descriptor which is going to be a crucial physicochemical parameter, which is going to be the governing parameter for thinking about the oxidation activity. Okay, so if I can control this, okay, I can control the oxidation activity. So this physicochemical quantity is called a descriptor. Okay, in this case, so I'm going to think about a way of modulating the descriptor here. Okay, so if in this case, let's say I take a host oxide, zinc oxide, my vacancy formation energy is about 3.3 eV. Okay, so what is the reaction I'm thinking about? So I first calculate using density functional theory the total energy of this system. Okay, and then I have formed oxygen in the gas phase. So what one oxygen atom has given rise to half O2. I'm calculating the energy of this system using density functional simulations. And what is left out here? So there is an oxide with a vacancy. Okay, so there are three calculations involved: the total energy of this system, total energy of oxygen in the gas phase. I'm going to use half O2, and the total energy of this system. Okay, so this is going to give me the oxygen vacancy formation energy. Okay, as bond breaking is involved, it is an endothermic process. Okay, so 3.3 EV is involved in in this reaction in an undoped system. Okay, so first I do this reaction inside the computer in just plain zinc oxide. I am having 3.3 EV is required to form in a host oxide, that is the zinc oxide. So what is that? So this is a descriptor for oxidation activity. Okay, so that's the logic here. So when I dope this host oxide with all the alkali metal atoms, okay, so I'll say there are two parts to it. Okay, there's slash and there's I've marked it red. Okay, so typically what is your chemical intuition? Okay, when I dope this oxide with either lithium or sodium or potassium or rubidium and cesium, all these things are monoatomic. They have oxidation states of +1. Okay, so in this host oxide, the oxidation state of zinc is +2. If I replace a host cation, +2 cation, with a +1 metal, okay, typically what the intuition suggests that there will be a hole on the all the electrons that are required for oxygen is not, these dopants cannot give adequate electrons required for the oxygen. Okay, so all of these metals, all of these dopants, okay, will decrease the oxygen formation energy. So when I dope zinc oxide with these things, what am I doing? I am making the oxide a better oxidant. Okay, okay, and then what does this indicate? This indicates the tendency. See, when I have just to go back. Okay, so when experimentally I prepared a doped oxide. Okay, then when I make this doped oxide, there is no reason to believe that this dopant will be on the surface. It can also be on the subsurface region. Okay, see, all the activity for heterogeneous catalyst is on the surface. All right, so if the dopant is not on the surface, if it is segregated to the bulk, okay, if it is in the bulk, it is not going to be useful for oxidation. Okay, okay, so whatever, if the dopant is segregated to the surface, then it's going to activate these oxygen, which can be used for a reaction. But if it's segregated to the bulk, if it's in the subsurface region, it's not going to be useful. Okay, so these things which where I indicate with a slash are those dopants which segregate to the surface regions. Okay, that's what I'm indicating here. All right. So okay, so what was this? This is again a computational screening. Is involved here. So I'm exploring different dopants, and again there are two coordinates. Okay, two coordinates. One coordinate is indicated by the color, okay, of the thing, whether I'm coding it red or blue, right? I'll elaborate. Okay, when you look at the numbers, you should be, and with your chemical intuition, you should be able to tell what this dopant is doing. Okay, so as opposed to, let's say, lithium atom, I am putting in, let's say, cobalt atom, okay, or iron atom. Okay, iron is a dopant. So iron is a it takes, let's say, ferric oxide, Fe2O3. Okay, so typically iron takes a higher oxidation state compared to +2 state. Okay, the host oxide is, let's say, +2 state, whereas iron is typically in a higher oxidation state, more than +2, +3 or +4. That will increase the vacancy formation energy. Okay, when I add, let's say, iron to the system, it binds better. The binding energy of oxygen is increased, okay, compared to binding energy of oxygen in the zinc atom. Okay, so I am making it worse oxidant. Okay, so what does this computation screening do? So I replace in the host oxide a variety of dopant, okay, to modulate the oxygen vacancy formation, because we are thinking about oxidation activity in terms of oxygen vacancy formation energy. And when I increase, okay, so when I make it blue, that means I'm making it a harder oxidant. Okay, when all these dopants promote oxygen vacancy formation, I've coded it red, and all those things which are making oxygen vacancy formation more difficult, I've coded it blue. Okay, for example, titanium is going to make it very hard. Okay, titanium, if you see, okay, is a very strong oxide. Okay, so when I put titanium when I dope the system with titanium, the oxygen vacancy formation energy is increased from 3.3 to 5.5. Okay, all right, and then part of these dopants, for example, all these dopants do not go to the surface. There are some dopants that may go to the surface. Much of these dopants are segregated to the bulk. Okay, so their influence on oxidation activity will not be that great. Okay, so so this entire screening, okay, was if you're interested, you can look at this manuscript. So this, what is that we tried to do here? So this is a way of screening for oxidation catalysts. Okay, so which of the dopants make the host oxide, in this case the host oxide is zinc oxide, promote oxygen vacancy formation energy. All these things which are coded red promote oxygen vacancy formation energy. All these things which are coded blue make oxygen vacancy formation more difficult. Okay, increase the oxygen vacancy formation energy. Okay, so this is one way of screening. All right, so conclusion one is we have identified dopants that promotes oxygen vacancy formation. Okay, surface oxygen vacancy formation. If you can do that, what does it do, okay, for you, okay, in terms of actual reaction mechanism? You are promoting Mars and Van Crevelen oxidation. Okay, I've elaborated this in the some previous lecture. So there are three mechanisms you must have seen from your CRE class. Okay, one is Langmuir-Henshelwood, Elie-Riedel, and the third is Mars and Van Crevelen oxidation. Okay, so how do you think about this? One, as soon as you computationally evaluate, you should be able to think about what kind of experiment I can do to test your hypothesis, okay, which you generated from your computation. Okay, temperature program reaction. Okay, this is a class of experiment that is available in most of we have it in our department. So that can be which will tell you. Okay, so you increase the temperature of the system, let's say doped oxide, and as a function of temperature, you ask how much oxygen is obtained, how much oxygen comes out of the oxide. Okay, as you keep increasing the temperature, oxygen will come out of your doped oxide. Okay, so when you have the doped oxide is let's say it's a very good oxidant, the oxygen will come out at a lower temperature. If it's a bad oxidant, it will come out with at a higher temperature. So how do you envisage this experiment? Okay, first I do this reaction with this experiment with zinc oxide. Okay, and I calibrate at what temperature oxygen is evolved from this undoped system, and then I put a doped. I do the same experiment with the dopants, and then to get at what temperature oxygen comes out, and you compare your reaction, experiments with the computational screening that I mentioned before. Okay, so you should have some maturity to think about. You should be able to talk to experimentalists. How do I also test the hypothesis that I've generated from my computational study? Okay, so lesser oxygen vacancy formation, oxide is reduced at a lower temperature. That's the goal, right? So we'll move to another case study here. Okay, so if you look at the periodic table of dopant, when I have a titanium dopant, you will see this. I mean, see, unfortunately, you're not on campus. I couldn't. I cannot demonstrate these things, but let me see whether I can do it. Okay. So what are we seeing here? Okay. So I'm plotting the electron density. Okay. This is an important output from a density functional theory simulation. I am plotting the electron density for a titanium doped zinc oxide system. When I do that, titanium is 4+. Okay, that is, zinc oxide is 2+. What do I mean by that? There are 2 valence electron in zinc, whereas titanium, its electronic configuration is D2S2. So it has 4 electrons. Okay, so when I put titanium onto zinc oxide, I have excess electron density around titanium. Okay, so that I was postdoc at this time. We were looking at this computational experiment, and what I thought was when I have this excess electron available around titanium dopant, what will that do? Okay, we were for this Mars-Crevelen mechanism was first documented in 1963. Okay, so this is the dominant mechanism that was shown for all oxidation mechanisms. Okay, so I got into a lot of controversy when I did this work. Okay, so I proposed a completely different mechanism for thinking about oxidation reactions. Okay, so my thinking was the following. Okay, instead of creating oxygen vacancies, I can think about a completely different mechanism that is different from Mars-Van Crevelen mechanism. I'll illustrate here. Okay, so instead of creating oxygen vacancy, this excess electron density can be utilized for absorbing O2. Okay, onto the dopant. Okay, so think. Okay, just go back to few slides. Okay, back. Usually in mass and covalent mechanism, I'm thinking about this oxygen atom is given off to the reactant. Okay, to oxidize the reactant. So I'm forming an oxygen vacancy. I'm not thinking about that here. Okay, I'm not thinking about oxygen vacancy formation. I have a titanium dopant. I know there is an excess electron density available. I'm using that excess electron density to bind to oxygen molecule from the reactant. Okay, so for example, let's say carbon monoxide oxidation. The reactant has carbon monoxide and O2. That O2 is bound to the dopant. Okay, so what am I plotting here? What am I not plotting? What am I indicating here? Let's say I substitute different dopants to the host on different substitution of dopant onto the host cation site. Okay, this is a zinc site. These are all zinc site. Onto the zinc site, I substitute different dopant atom. Okay, when I substitute, let's say aluminum, my absorption. So I'm talking about absorption energy. Okay, of O2. Okay, when I substitute titanium, energy increases. Let's say make it okay. When I substitute titanium, so the negative numbers means I am making it the reaction absorption energy is favored. Okay, O2 absorption is favored. Okay, so if you have questions, we can discuss all these things in the discuss the questions in the absorption discussion hour. So I am facilitating oxygen absorption when I have aluminum, titanium, vanadium. Okay, dopants. Okay, aluminum oxide, it's a +3 dopant. Titanium oxide, it's a +4 dopant. Vanadium typically it's a +5 dopant and so on. Okay, all these things facilitate oxygen absorption. Whereas magnesium, yeah, it's a +2 dopant. It doesn't facilitate oxygen absorption. Sodium does not facilitate oxygen absorption. Okay, and then in the next, so what am I illustrating here? I'm illustrating a catalytic cycle. Okay, so in the next reaction step, one of this oxygen is removed. Okay, and put in the gas phase half O2. What am I envisaging here? I'm envisaging this oxygen atom is used for oxidation. All right, instead of oxygen coming by formation of oxygen vacancy, I am getting oxygen from this absorbed oxygen. Okay, again, so these indicate the energy for a variety of doped oxide system. Then I can envisage for this system, I can envisage O2 being absorbed. Okay, one more O2 from the gas phase, and so I found something like a O3 complex. Okay, and then what do? I again, this one of the half the oxygen, one of this oxygen atom is given off to the reactant for oxidation. Okay, so what have I managed? Okay, this is called a catalytic cycle. Okay, let's understand what's a catalytic cycle. It's an important slide. You have to understand this very clearly. What is a catalyst? From your high school, you have learned a catalyst is something when you say that doesn't change. Okay, catalyst is something doesn't change during the course of the reaction. Okay, is this true? This is partially true. Okay, so what do you mean by partially true? If the catalyst doesn't change, what is the role of the catalyst? Okay, the catalyst does change. Okay, but during the course of the catalyst cycle, it regains its state. Okay, so let's say this is the catalyst. Okay, a dopant which is bound to absorbed oxygen. Okay, during the course of this reaction, there's a catalytic cycle. When you say cycle, means there's a cyclic process. Something changes, but that change is reversed during the course of the reaction. Okay, so this catalyst, this O2 molecule, one of the O2 is given off to the reactant that is being oxidized. O2 is gained, and then again one oxygen atom is given off. Okay, during this cycle, I have managed to come back to my initial state. in that manner, I have regain my state, okay? But during the course of the reaction, catalyst does participate, okay? So it does change, but it does change in a cyclic manner, okay? So reactants have an irreversible change, okay? The reactants irreversibly change to a product, but a catalyst reversibly changes, okay? In a way, when it changes to some other, in this part of the cycle, when it changes, that change is reversed in this part of the cycle, okay? This is what you mean by catalyst cycle. Again, so Sabatier tells you what, okay? So if you want a good oxidation catalyst, all these steps should have less activation energies, okay? If this step is very facile, okay, if this is very easy, that's not going to make you a good oxidation catalyst. That's going to make you just a good oxidant, okay? But for you to have a catalytic cycle, all these steps have to be balanced, okay? If this is very easy, typically this oxidizing the reduced catalyst is going to be difficult, okay? So that's the way we are exploring, okay? We computationally added different dopants and try to look at the energetics of the entire catalytic cycle to predict what's a good oxidation catalyst, okay? Again, so how is this? We're going through how this kind of study is being done. So what is that? I have a doped oxide and then I'm adsorbing. This tells you the energetics, aluminum and titanium, how the energetics of adsorption, okay, negative energies, okay, mean it's an exothermic process. The adsorption is facile, all right? And then in this thing, I'm talking about carbon monoxide oxidation, okay? I want to oxidize carbon monoxide to carbon dioxide. In the next step, I'm adsorbing carbon monoxide and then I'm forming this kind of thing, O2 from already I have adsorbed O2 and then I have adsorbed carbon monoxide. Carbon monoxide, here, carbon is indicated by this red atom. The green atom indicates O2. And I'm talking about the energy of that step, okay? And then what is that? In the next step, I have oxidized, I get carbon dioxide, okay? I have taken carbon monoxide and then I've oxidized carbon dioxide, carbon O2 here, okay? And then I am left alone with one add atom of oxygen adsorbed to a dopant. And then in the next step, what am I doing? I mean, again, I'm talking about energies here. And then I'm absorbing carbon monoxide. And then I have obtained one more carbon dioxide. What did I, so this is the entire catalytic cycle. So what did I start with? See, to start with, I had a doped oxide system. I just had a dopant in an oxide. And then I added reactants. What are the reactants? Carbon monoxide and O2 are the reactants. And I've gotten two carbon dioxide, okay, molecule, two products, okay, two carbon dioxide. I've added two carbon monoxide and I've one O2 and gotten two CO2 molecules, okay. So, and then I calibrate the energetics along different catalytic, different steps of the reaction cycle here, okay. So I can envisage different kinds of mechanisms here, okay. So for example, compared to the previous slide, the first two steps are same, and then I can have different, I mean, you can compare it, okay. You can contrast, okay. You have the PDF with you. You can contrast what is different from the previous second in the review article which I've sent you. These are adjacent. There's a slide. There's a schematic which compares the two different. In what way this differs from the previous thing. Okay. So see, actually this differs in this step. Okay. Here I'm absorbing carbon monoxide, but in this mechanism I am okay. There's a typo here. Okay, I'm absorbing O2. Okay, it's not carbon monoxide. I'm absorbing O2, and then from that O2, okay, I'm this is like an O3 complex. I'm getting going to get carbon dioxide in that next step. Okay, and then again you can think about different schematics. So I mean different schemes. Okay, here in this step, I'm after having this step, I'm absorbing one more carbon monoxide. I'm forming something like an oxalate complex, okay? And then from here, I can form oxalate, okay? Kidney stones, okay? Or actually oxalate complexes, okay? So from, I can decompose an oxalate. Oxalate is, there are CO2, there are 2 molecules of CO2, okay? And I can decompose the oxalate and get carbon dioxide, okay? So you get, how do you do this study? Okay? I envisage different reaction pathways and explore the energetics of different pathways, okay? That's the, so what does the theory predict? I have predicted, okay, we predicted a non-mass van Crevelen mechanism. Okay, this was very controversial whenever I used to go to conferences, there were lots of questions. People were opposed to this kind of study, okay, because it was very, very controversial at that time, okay. So because this from 60s, okay, early 60s, this Mars van Crevelen was accepted mechanism for oxidation, okay. We come and propose a different mechanism altogether in certain class of catalysts, and then so for it to be a good catalyst, the activation barrier should be small, right? So that's what makes a good catalyst, okay? So whenever you propose something, especially when you propose something debatable, okay, the onus is on you to check via experiments, okay? So it was very interesting. We also wanted to publish it very quickly, but we knew that when you propose something so controversial, the onus is on us to demonstrate this experimentally, okay? So I took a long time. I worked with a lot of experimentalists, okay? So this is something which you all should, so you may go and do research in some places, or you may go to industry, okay? So one of my students is working in Reddy's lab, okay? He did all these simulations in my lab. Density fractional theories is a dual degree student. He did computational study, and then he was hired in Reddy's lab, okay, after dual degree, completing his Reddy's dual degree. So there, it is not enough to just predict something, okay? You should have the capability to work with other experimentalists, okay? The experimentalists may not know what is the right kind of experiment that will accurately test your prediction, okay? You should have the maturity to propose what is the right kind of experiment that will test your theoretical prediction, okay? So I worked with a lot of, so this is a typical, okay, if you come to my lab or Professor Gautam Dev's lab, okay? These are standard experiments that are available in Shiva's lab and so on, okay? So these are all available in your heterogeneous catalysis labs, okay? They would have a reactor, okay, packed bed reactor, differential reactor. You must have heard all these things in your CRE classes. And then there can be an inline, okay? The products that are coming out of the reactor can be detected via a GC, and there can be an FTIR that helps you understand what are the reaction intermediates involved, or in a more sophisticated system, there can be a mass spec also, okay? All these things are possible, okay? Many experimental proofs that are available in a typical heterogeneous catalysis lab, okay? So, all right, so, okay, so we also predicted very interesting things, okay? For example, instead of, it is elaborated in the review article. We also said that there is a very interesting mechanism. Once you have a doped oxide system, instead of this dopant interacting with gas phase oxygen, okay? Gas phase oxygen, there is a dopant on the host that can migrate to this dopant, okay? So we proposed this, okay? And then that can go here, and then you are creating, see, is this mass van Crevelen or not mass van Crevelen, okay? You are creating an oxygen vacancy because this is like a mass van Crevelen because you are creating an oxygen vacancy here, okay? But you're also, the oxygen that is being used is the adsorbed oxygen. It is not the host oxygen, Okay, so these are all, this is a very interesting study. I mean, I like this study a lot. Okay, as a postdoc, these are 10. I worked with so many experiments, 8 experimenters. Okay, to look at this in detail. Okay, it took a long time to nail down. We did lots of using isotopic oxygen. Okay, lots of interesting results came out of this study. It's a very interesting study. So all these things are mentioned in the review article. Okay, this activation energy, okay, was only 0.2. Okay, so as I said, one number as engineers you should always remember as a chemical engineer is 26 milli electron volts. Okay, that is the KT at room temperature. Okay, if you have taken any class with me, you would have heard this number again and again being mentioned. Okay, so when you say something is large or small compared to what? Okay, so here we are thinking about 26.026 is the KT. Okay, at room temperature. So this is the typical binding energy. Okay, covalent bonds have 1 eV. Okay, that is the number you should have in your mind. 1 eV is about 100 kilojoules per mole. Okay, the typical, when you say good covalent bonds, strong bonds, okay, have 1 or 2 eV. Okay, that's the bond energies. So 0.2 V is a small number. Okay, this is very easy to do such processes. Okay, so that can explain. We did lots of isotopic study. Okay, so this not O16. Okay, CO2 formed from O18. Okay, so this are elaborated in the review article. So we said where it will occur, where it will not occur. Okay, so this is very important. Okay, so so what am I trying to say? Okay, it is not enough for a computational scientist to just say, oh, I have this result. You should have the maturity to work with experimentalists to propose the kind of experiments. Okay, in this case, we proposed an experiment that can be conducted with O2 molecule, but both these oxygen are isotopic oxygens. Okay, so O18. Okay, so as opposed to O16. Okay, so these are isotopically labeled. So we can detect what kind of O2 from mass spectrometry. Okay, we can detect a different CO2 which have different molecular weight, and then we can calibrate the effectiveness of this mechanism. Okay, this is one of the see, we do many computational studies. Okay, not everything. I mean, when you publish, not everything is published along with experiment. But when something is very controversial, it's going to be debatable. Okay, you have to convince yourself of the validity of your computational study. Okay, ultimately, experiment is the king or queen of research. Okay, so that is going to tell whether your computational study is valid. Okay, so you should have the patience and maturity to design what kind of experiment that will accurately check calibrate your mechanism that are being proposed from computations. Okay, just to conclude this part of this lecture, we propose a new mechanism which is different from the textbook mechanism. Okay, from textbook Mars and Van Creveld mechanism, we supported this mechanism with carbon monoxide oxidation system. This very important class of oxidation because carbon monoxide is a poison. So the experiments also suggest an oxygen shuttle mechanism. All right, and then okay, so again, this is all elaborated in the review article that I've sent to you. So just to give you some more, just an advertisement. Okay, to just tell you how you think about doped oxide system in some other context. Okay, so as I said in the first few slides, modulating selectivity is an important goal in heterogeneous catalysts. Okay, we asked this question. Okay, in the previous study, there's only one carbon monoxide can get oxidized to carbon dioxide. There's no selectivity. Okay, if you have H2 and carbon monoxide, then there's a question of selectivity. Okay, so we will look at some other system here. Can doping influence selectivity? Okay, so this is we used methanol as a chemical probe. Again, methanol to formaldehyde. Okay, this is an important system. Okay, in chemical process industries. So we are looking at whether dopants can influence selectivity of methanol dissociation. This is the first step in any, see, sometimes it is, you may not be able to study all steps, okay? You may able to study one important step that might be a rate determining step, okay? That's the way we were thinking. Can dopant influence one particular step of reaction pathway, okay? For example, when I have methanol, methanol can dissociate in, I'm thinking, let's say, different dissociation pathway, okay? CH3OH, I can dissociate the OH bond, or I can break the CO bond, okay? So what I have a methoxy radical, and this OH, okay, that H that came from OH bond, that H is absorbed here, okay? Okay, what am I representing? This is a small fragment of the catalyst, okay? I have a host oxide, again I have a dopant. I have, I am absorbing methanol. This is a dissociative chemisorption. What do I mean by that? As I absorb methanol, I am dissociating a particular bond, right? I form a methoxy radical and a OH moiety here. As opposed to this pathway, I can dissociate carbon, the bond between carbon and oxygen, okay? I can break this bond, or I can, here what have I formed? I have formed formaldehyde, okay? Methanol has been converted to formaldehyde. For doing this, what should I do? I should break one of this bond, that is one of the methyl, CH bond from methyl, and I have absorbed that H, which I obtained from breaking methyl CH bond onto an oxygen. And simultaneously, I have also broken the OH bond, okay? There are two bonds that have been broken. One hydrogen is here, another hydrogen is here, right? So what am I, okay, so what's the goal, okay? So when I have methanol in a doped oxide, on a dope oxide, when I supply methanol to a doped oxide, I can form different products. I can form, let's say, formaldehyde. That's one pathway. Here, this pathway is very important for what is called dimethyl ether. Okay, this is an important fuel. Okay, dimethyl ether is an important fuel. Okay, I can start with methanol. I can form dimethyl ether for that product. Okay, this pathway is important. I can start with methanol and form ethane. Okay, that is a damn important product. Okay, so how do I form ethane? I have a methyl moiety here, CH3. If I have another methyl moiety on the surface, the two methyl moiety can collide in, let's say, Langmuir-Henschel mechanism and form desorb as ethane. Okay, that is important. Okay, that pathway is probably occurring in this. Or the third pathway, okay, where methanol is forming formaldehyde, is occurring via this pathway. So what's the question I'm asking? Okay, the question we were asking is, if I have a dopant, how would the dopant modulate my reaction pathway? Would I facilitate this pathway or this pathway or this pathway? Okay, that's the question we asked. Okay, so I have a host oxide with a zinc oxide, and I used a variety of dopant. Okay, again, so okay, so here I'm forming DME. Okay, DME, dimethyl ether. Okay, that's the, for DME, this is the pathway that is important. For ethane formation, C2H3, this is the important. This is the important reaction pathway. For formaldehyde, this is the important reaction pathway. What's the, so how do I do this computational screening? I first compute the this energetics of this bond dissociation in the host oxide. Okay, in zinc oxide, this energetics, the energetics of this pathway is, let's say, negative 0.7. Okay, and then this is for this pathway, it is negative 0.4. All these things are elaborated in the review article. Okay, this is going to be endothermic. Okay, negative means exothermic, positive means endothermic. It is going to be hard in host oxide. Okay, then what do? I dope this host oxide with dopant, different dopant. For example, I have titanium doped zinc oxide. What have I done? The titanium doped zinc oxide promotes this pathway, okay, makes this more negative, okay. But however, in contrast to this, titanium suppresses this pathway, okay. From plus 1.6, it has become 2.4, okay. There's more endothermic, okay. So titanium promotes this pathway too, okay. But this suppresses this pathway, okay. And then aluminum also promotes this pathway, suppresses this pathway, okay. In contrast to that, I have, let's say, okay, just imagine, these are all, let's think about, you should build your chemical intuition, okay. This is 2 plus, this is 3, aluminum is 3 plus, titanium is 4 plus, okay. So as opposed to that, I am substituting with monovalent cations, okay, K, potassium and sodium, okay. So what does this doped system do, okay? It suppresses this pathway from negative 0.7, it is less negative, okay. Whereas this promotes this pathway, okay. So when I have, let's say, alkali metal doped zinc oxide, my chances of forming formaldehyde is higher, okay. But my chances of forming ethane or DME is lesser, okay. So this is a way how a dopant can modulate. See, in an undoped system, there are 3 pathways. The question we were asking is, how does dopant modulate these pathways, all right? Again, so this is a very interesting hypothesis. I mean, by the time I mean, I wanted to check this. When I finished my postdoc and I joined IIT Kanpur, okay, we didn't have time to look at this experimentally. Okay, this is an extremely important prediction. Okay, I mean, it's not important, interesting prediction. All right, for us. Okay. So whether methanol can form formaldehyde when I have this dopant, okay, as well as when I have, let's say, titanium aluminum dopant, do I see increased DME, okay? All right. So the activation barrier for this, okay, this is a very important product. So we also computed the activation barrier. Again, these activation barriers are very small, okay, 0.2 is these are all very small numbers, okay. So even though you're breaking 2 CH bond is broken, OH bond is broken, this looks like a hard pathway, okay. But when you have this dopants, this pathway is promoted, okay. That's the computation prediction, all right. And then again, it's once you do one of these dopants, it's easy to screen, okay, for other systems. And then we explored a variety of things. And then, okay, so what is this color code? Okay, the color code, when it's red, that means it's very facile. When it's blue, it's suppressed, okay. So contrast, this is very facile. This, when I have this dopants, this pathway is very facile, okay. These dopants suppress this pathway, okay. These dopants, for these dopants, this pathway is very facile. Whereas this pathway is suppressed, okay. So that's the way you think about how do you design newer systems for different catalytic systems, okay. So just to give you, this is the last slide. So in this lecture, what have we done? Okay, we have elaborated how different dopants can be computationally screened to change the oxidation catalytic activity of zinc oxide surface, okay. I have a host oxide, I use dopant to modulate the catalytic activity of the oxide. We proposed an important mechanism, which is called it's not a textbook mechanism, non-mass equivalent mechanism, where it's not the oxygen vacancies that are important for oxidation activity. It is the adsorbed oxygen which is going to contribute to your catalytic activity. Okay? So we demonstrated this computationally first and then experimentally later. We demonstrated this for CO oxidation, preferential oxidation, okay, in a stream of CO and hydrogen. We also demonstrated, we did some computations on methane activation, okay. Methane activation to methanol. It's a very, very important reaction for gas to liquid technologies, okay. Because most of this gases, okay, it's hard to transport. If we can transport methane, okay, as a liquid, okay, transportation of liquid fuels is much more easy. So one of the liquid fuel which you want to get from methane is methanol, okay. And we looked at trends in activity computationally. We also, in the last slide, I told how can dopant affect the selectivity for methanol decomposition, okay. So from both these things, okay, what did we try to do here, okay? We tried to, in the previous thing, we explored, we gave a first cut introduction to density functional theory and how it is applicable to doped oxide, and how do you screen doped oxide for different catalytic systems that are important industrially, okay? Carbon monoxide oxidation, preferential oxidation of carbon monoxide, methane activation, and methanol activation, all these things, okay? These are all elaborated in the review article, okay? Let me stop here, all right? If there are questions, we can discuss all these things, all the questions in the discussion